Hi, everyone. Thanks for joining our Women Who Code podcast. Welcome to the show. I'm Eliza Sarobhasa. I'm a Women Who Code Leadership Fellow at the Python track. It's nice to meet you. My pronouns are she and her. Today, we're meeting with Danica Marsden. She is a principal quantum computing scientist at Bank of Canada. And our topic for today's show is from astrophysics and discovering new galaxies to building and using quantum computers. So Danica, welcome. It's nice to chat with you today.
Thank you very much. It's nice to be here.
So Danica, she received her Bachelor in Science in 2005 in combined honors physics and astronomy, followed by a PhD at the University of Pennsylvania in experimental cosmology, building cameras and telescopes to study for the universe. Following her PhD, Danica accepted a Keek Institute for Space Studies Fellowship at Caltech and has worked with the research group at UC Santa Barbara as a postdoctoral scholar, continuing her work on novel technology for astrophysics. Same time, she also taught astronomy classes at the local Santa Barbara City College and has a small electronic assembly business. To this, she switched gears, working new technology development at Suncor, also Petrocan, from 2013 to 2015. So that's a recap, and now we'll get a little bit more up to date. So 2015, Danica was recruited to quantum computing, working as a technical project manager for D-Wave Systems, building quantum annealing computers. In 2020, she moved to a role with the SQT lab at SFU. Oh, you're in my city. And startup Photonics, working on building universal quantum computers with Dr. Stephanie Simmons. In 2021, Danica was recruited to the Bank of Canada to develop their first quantum strategy, that's exciting, program and roadmap, as well as apply quantum computing to central banking. So Danica, welcome to the show. Is there any points that I missed or anything else to add update, your hobbies or favorite plant to garden that you'd like to add for your bio?
I love animals. I'm a proud cat mama, and I do a lot of adrenaline sports. So I rock climb and I ski and things like that.
Is there anything else you'd like to discuss about your career history, like why you chose this field, when you were back in school?
So I'd say it was sort of philosophically driven. I was very curious about the world and the universe, and I was always fascinated by the questions: what is out there? How do we know what we know? Which really sort of ultimately led me down this path towards building detectors and cameras and telescopes to study the far universe, because ultimately the only information we get about the universe on the largest scales are these photons, particles of light that arrive here at the Earth after traveling for billions of years. And so how we collect that light with the detectors and the cameras and the telescopes, and then how we process and analyze that information, is sort of the source from which we derive all of this knowledge. And getting to the crux of that and doing it myself and understanding it myself drove me. But in hindsight, when you look at my path, it seems really straightforward. But in fact, I think, as is so often the case in real life with people, it was a little more windy than it might at first appear.
When you were in undergrad, did you know which major you wanted to go in, or was something you were kind of exploring? Because I know when we're university students, they want to know to do the rest of their life, and it seems like a very big decision.
For me, even a lot of these questions start to come up even in high school. What are you going to do now that as you're leaving high school? And in school, I really liked the clarity of math. You're right or you're wrong. There's no sort of opinion about it. Whereas in the social science and English and arts, things like that, there was definitely more of an opinion-based merit. And so I really liked that clarity. And then I actually originally thought I was going to go do a degree in science and engineering and go and design crazy planes for the Air Force, that kind of thing. I had really liked Top Gun when I was in school. And so I thought, wouldn't it be cool to design those kinds of planes and maybe fly them too? So that's how I started. And then, of course, life intervened. So I actually did my first year of university in general science, and I was actually really bored.
Right.
Well, just these large survey courses, generic calculus, there's no sort of application yet. And I think a lot of people get lost in that, as did I. So I actually quit after my first year and I became a ski instructor in
Nice.
Australia and in Canada. And so I took that little bit of time off. I tried some other things. And then
Mhm.
after a year or so, I thought, I do miss that intellectual stimulation. Okay, I'll give it one more go. And in my second year, I started to get to study, see things like relativity and quantum mechanics and things
Mhm.
like that. It started to get a little more interesting, and I could see more applications. Mhm.
Right.
I don't think I know a single person who hasn't had a moment in their life of what the hell am I doing right now? And I think becoming skilled at, when you're in those moments, figuring out, having a process for figuring out where you're going to go next,
Mhm.
which entails usually a bit of research, talking to people, networking,
Mhm.
talking to people who do jobs that you've never heard of or jobs that you don't know what they entail, things like that, traveling, trying working at different places, and giving yourself that room to discover, I think is important for everybody. And it never appears as though successful people are doing that, but I can almost guarantee that everybody's gone through that at least once in their life. It
Mhm.
keeps happening. I mean, it'll happen again after undergrad sometimes, after grad school, after you finish with a job at a particular institution.
So you found your passion, you finished undergrad and got you, but then what made you decide like higher education, like post grad, like you want to do how they term states like a graduate student, grad school?
Mhm.
Yeah.
Here we go again. So I
Mhm.
was, when I was in undergrad, I wound up taking a physics course, which had a couple hundred of students. And
Mhm.
in the spring, there was a professor who was walking by me one day in the hallway and said, "What are you doing this summer?" And I said, "I don't know." And he said, "Do you want to come work in my lab this summer?" And I said, "Sure, I need a job." And it turned out that he built telescopes. And so
Oh
I wound
wow.
up working in his lab for the next several summers during my undergrad and learning how to solder and machine and write code and all those good things that are effectively what most people think of as engineering, but is also encompassed by physics, certain parts of physics. So yeah, and I think this happened to me several times where there was somebody who sort of saw my potential. And when especially when you're young, or if you're changing fields later in life, you don't really have this track record yet to point to.
Mhm.
You know your potential and your desires, and you sort of have to push past any naysayers. It's very
Mhm.
easy for people just to say, like, what do you think you're doing? But later in life, ultimately, you do have this track record that you can point to, or that can even hold you back because you think, okay, this is who I am now. But yeah, so at that point in time, I was very fortuitous to, sometimes in life it's like that a pinball machine, right? Where you just
Mhm.
are going along in one direction and then somebody influences you. So this
Mhm.
was one of my key characters, this professor. And so I worked with him for several years. And actually later when I left his lab, I was curious. I said, of all the students, why did you ask me? And thinking that he was going to say, oh, I was trying to promote diversity in physics or something like that. And he said, oh, no, you actually tied for the top score on the final exam, but the
Wow.
other person was much more awkward.
Oh.
So, um, so yeah, sometimes just these things happen and are present opportunities. And then after my undergrad, I was backpacking around Europe for 6 months,
Nice.
giving myself some time to figure out what to do next. And that same professor said, hey, what are you going to do next? And I said, I'm not sure yet. And he said, have you thought about grad school? And
Mhm.
I said, I can't afford grad school. And he said, oh, no, no. In the sciences, if you get in, they pay you. And I said, oh, that changes things. So I applied to several schools, and I knew that if I was going to go do that, I wanted to do experimental cosmology, carry on with building telescopes and studying the far universe.
Yeah.
And so I only applied to programs where there was already a professor doing that, and I had contacted those specific professors to ask, what they had, what kind of work they had, and projects. So I think that's important. A lot of people think that you just apply to a program at large, but I think it's actually important to realize that the person who will ultimately be your boss or thesis advisor is an
Mhm.
individual, and you kind of need to do the research to seek out who those individuals are, what they work on, and get excited about the potential projects, because you need to have that connection. So even if you get inside a grad program, you still need to connect with a professor in a lab or, yeah, an advisor. in
And
order
it's
to
focusing
continue.
like, yeah, if what their mission or goal is similar to what you want to work on. Did you have a favorite person that you applied for? Or did you narrow it down to like two great people, or did you based on like, previous projects they work on or something, it was a future project, you're like, oh, shiny.
Yeah, there were several great people. There was one lab that was focused more on software, and I knew I liked building things, and I felt that I was good at that. And that was sort of a special skill set. And then it kind of ultimately came down to the cities, because there were two really great labs doing similar projects. The professors were both great, and the other students were both great. And then it just sort of came down to the city that I felt more comfortable in. But it's hard to have set criteria to make these decisions. Sometimes you just have to go through gut.
Everyone's so awesome, so it's hard. I agree. As a segue, like, how do you keep up to date? Just like, who's working on which kind of project, right? Or that like, oh, this person will be building like this kind of telescope, and like these are materials that will go into like building it.
Right. Okay. So yes, in that realm of the universe, being groups who work on things like space telescopes or large ground-based or balloon-borne telescopes, there aren't that many people working on that stuff. And there's a website called The Archive, and it posts for free a lot of papers. People put their papers that will be published online there. And over time, if you follow, there are different threads. So there's one for astronomy and cosmology. And if you just follow over time, you'll realize the same names come up over and over. And so there are these, I'd say in the States, maybe on the order of, 20 big labs, especially the hardware part, it's expensive. And so all of this comes at a cost, and they need to get grants in order to do this kind of research. And so you have, maybe about 20 big labs that are able to participate in these larger physical experiments. And then there will be many other groups or professors who, I think in Canada, there's same thing. I think, there are a couple of larger groups at the larger universities, and then there are some smaller institutions working more on the analysis or the theory, things that don't require so much money, because these telescopes take millions and millions of dollars to build. So they have to get the funding for that. These things are very specialized. And so once you kind of get into that network, you realize, okay, there's one group, one very special group who, for example, in Cardiff, there's one group who they are the experts at making lenses out of a particular material for doing observations in microwave wavelengths. So it's a very specific niche. So if you're going to build a telescope at those wavelengths, that's who you go to get your lenses. I mean, it's just kind of, that's known, right? So it's like that. There's usually only one or two vendors of particular things, and people get known for particular things. So for detectors, one of the big places that that work on detectors, fabricating them for the first time, or and that have foundries are, so the Jet Propulsion Laboratory at NASA, for example, is involved in a lot of these projects. They help fabricate things. And then you've got places like NIST in Colorado, the National Institute of Science and Technology. So a lot of people work there and do research, but they also, some of those people work on developing new types of detectors and other places too. But these are some of the key players, and you'll just see their names on papers and those institutions on these papers that come up over and over again.
Okay. It's really cool to learn. Thanks for sharing. Just adding on the observatories, did you have a favorite space observatory, or places like you have a bucket list that you want to visit but haven't visited yet? Doesn't have to be like a specific place, like because of like the air quality and like the height of the mountain.
Yeah, well, I worked on a telescope during my grad school years that was in the Atacama Desert of Chile in the Andes Mountains. So most ground-based telescopes, you really want to put them in places that are high, but also that are very dry, because it's water vapor in the atmosphere that will steal some of your signal that's coming in, but it will also emit noise in the same wavelengths. So you want to try to get above as much of the water vapor, and then just be in dry places away from the water vapor. And So I loved spending time there. There was really cool animals in the desert there. You know, we got to discover new galaxies and clusters of galaxies. So that was incredibly interesting. And then I did some follow-up observations on a radio telescope in Australia in a town called Narrabri, about 500 kilometers northwest of Sydney, called Atka. And it was an array of telescopes that were on these railroad train tracks. And so when they would reconfigure the telescopes, which they did while I was there, you could ride on the telescope as it was moving. And there were these sort of kangaroos jumping along beside. It was really neat. So sometimes, you know, astronomy can take you to these very remote, very interesting places. And then we also worked on some balloon-borne telescopes, which I found very interesting. Obviously, you can't go there up into the atmosphere or above the atmosphere, but I found those experiments very interesting because you're not doing a full space-based mission. You're just going on this huge balloon, these weather balloons above, and typically those are launched from the North or the South poles because the winds are circumpolar and they just sort of will circle the pole for about a week or two before they come down. Yeah, so very interesting. But there is one place that I haven't got to go, and so there are telescopes down at the South Pole. And most people don't think of the South Pole as a very dry place, but it is a very dry place. And so there are telescopes down there, and I would love to go down and see some of them.
All right, I'm just going to dial back a bit about your postdoc, Caltech, UC Santa Barbara, and it's correctly, Keck Institute for Space Studies. Did you have any like key achievements you'd like to share?
So I specifically chose to work with a professor at UC Santa Barbara on, and it was sort of based on work that he and others had done at Caltech on this new type of detector for astrophysics that they were developing called a microwave kinetic inductance detector. And prior to that, the detectors that were being used, say in Hubble and others, you'd have this array of detectors, and then you'd have to put a filter in front for, you know, if you want to know if the light is red, you have to put a red filter in front. And what that means is you're actually throwing away a whole bunch of the photons that are coming in. And when you're studying things, you know, galaxies billions of light years away, there aren't many photons coming to you in the first place. So it's a really wasteful thing to do, to throw all those photons away. And so what was cool about these microwave kinetic inductance detectors is that every single photon that landed, you could tell what its, you know, wavelength or color or energy was, which was different and unique. So it was, you could detect all the individual photons within a certain wavelength range.
And then, yeah, afterwards, if you wanted to edit in the data to remove like all the red ones, you could do that. Then we were able to collect all the information at once the first time.
Yeah. Right. Yeah. It was much more efficient. Yeah, I think a lot of people don't realize just how long, you know, to build up a solid signal of a faraway galaxy, how long you might have to wait to collect the light till you get a good enough signal coming out of the noise. And so how patient the older astronomers were, we'll say. And nowadays, as we develop these new types of more efficient systems, we're able to collect, you know, a lot more data more quickly. And this is what's allowing us to, for example, with the new James Webb Space Telescope and others, so quickly map out huge swaths of the sky relatively quickly, you know, over years instead of decades.
Like centuries and millennia and so on. So would you be able to share what your transition's like from academia to the private sector? So like, or the benefits or like the challenges for you?
Yeah, it was a tough decision, but as I was a postdoc, I was sort of evaluating, you know, postdoc is sort of this proto professor. And I was looking around and evaluating whether or not I wanted to really make that push and be a professor and stay in academia. And I decided that for the most part, what professors do wasn't really interesting to me. So,
get tenure.
Well,
depends.
It's more about how they get tenure, what they're spending their time on and day to day. And that was less exciting to me than other options. And so, yeah, I decided to go and try out the private sector. And so in terms of the benefits, I really liked my experience, both in larger as well as smaller industrial companies. You know, startups were really cool because you have the combined resources of the equivalent of several labs all together. So you'd have in a group, maybe something like 20 postdocs all together, and you could move really fast and get things done. That was really interesting. And then with larger companies, what I've liked is that they have the bandwidth to develop people and really optimize for good company culture, which has been shown to increase productivity and revenue by quite a lot. I think this is something that is not quite appreciated enough today, but it also benefits employees a lot. And yeah, I think these larger companies, startups, they're constantly just trying to stay afloat, so they don't have as much ability to focus on those kinds of things. But when you go to places like Google, the fact that you can spend 20% of your time working on whatever you want to work on, those kinds of things, right? That happens when you get to the bigger companies. But there are these trade-offs. So with startups, there's often this really strong passion, and we're a family and we're going to move really fast, we're going to change the world, that kind of thing. But then with these larger companies, there's a bit more of a nice feeling of balance that yes, I'm going to do really useful things, but I'm also going to be working reasonable hours and get to see my family, things like that. Yeah, and I think one thing that I learned too going into industry is that there's this idea that in certain spheres, maybe academia, maybe government labs kind of work, that you don't have to worry about selling things, whereas when you're in industry, it's sort of about the bottom line and selling things. But actually, when you think about it, everything is actually about selling. When you're writing grant applications, you're trying to sell yourself, and when you're trying to get good students to come work for you, you're selling yourself. So I think that's actually one skill that probably in hindsight I should have developed more when I was younger, was not trying to sell people things that they don't want, but just how do you, even transitioning between industries, how do you take this skill set and spin it so people understand the value over here, those kinds of things.
The transferable skill sets. And
well, selling really comes down to understanding what somebody else's needs are, and then determining, can I help get what that person needs, or do I know somebody else who can do it, etc. Right?
Okay. Yeah, I understand it when you put it that way. Thank you. And see, I'll cycle back on our topic for the podcast. How did you first start working in quantum computing?
Yeah, so when I was leaving academia, I had to go through, a period of research to understand what does somebody who comes from astrophysics, what can they do in the world, and what were my skills relevant for. And so I, sat down and had to think, and was thinking, okay, there are companies that do work in the space sphere or satellites or things like that make use of optics. And I made this big list of companies, and then I was thinking, okay, I also am interested in perhaps, energy related things, solar energy, those kinds of companies. And I applied to a whole bunch of different things. And I had thought about quantum computing as well. It was pretty nascent still back then. This was around 2013, I guess. And so I had actually, one of the companies that I had applied to was D-Wave. They were looking for ultimately a physicist, but at the time they had just hired somebody with the same skill set, more or less. And so I got a different job offered and followed this other path. And then a couple of years later, they came back to me and they headhunted me back. So that's something that can happen too, as you think. Sometimes you might not get the job at the time, but you don't realize that when the time is right, they might come back to you. So you can always keep that in your pocket. And yeah, they were really looking for physicists, particularly with good communication skills I had the experience with superconducting circuits and cryogenics and things like that were relevant to quantum computing, but they were looking for somebody who could be a technical project manager within that group of physicists and organize things and interface with clients. So that's how I wound up in quantum computing, and it was very exciting. Yeah.
And what do you think about the state of quantum computing today and where it's going?
So quantum computing today is maybe where, say, machine learning type, AI type things were 10 plus years ago. Very much still nascent. And currently, in terms of actual physical quantum computers, I'd say what's available now in the cloud are still very much prototypes.
Okay.
Many different companies are using many different types of qubits. So they're based on different physical systems. Some qubits are based on the spin of an electron. Some qubits are based on a loop of superconducting wire with particles going around the loop of wire. And there are other systems where they've taken ions and they've trapped them using lasers. So there's still not a consensus as to what the best qubit is. We'll say it's not.
It's an ongoing conversation.
That's not clear. So we're still very much in the experimental phase. But, you know, there are, I mean, what's on a little more sure footing are that there are these algorithms that exist already that we know will exponentially improve upon what classical computers do. And so one of them involves solving linear systems of equations, which shows up in many places in the real world. But the other one, it's called Shor's algorithm, and we know will break a lot of the encryption that we currently use to protect our, you know, healthcare data, financial data, et cetera. So for sure, there's a big push in that side of things with quantum, in the quantum sphere, which is, so NIST ran a challenge to discover new types of encryption that will be secure against quantum computers. So they've finished that and published these new encryption schemes. And so there's a lot of work now going into upgrading software to incorporate these kinds of encryption to be secure against future quantum computers when they come fully online. And then there are all these other techniques that we're going to be using, I'm sure, in terms of quantum sensing. So sensors that are better able to measure magnetic fields and things like that. For example, I know that recently there was a study that came out looking at using these types of sensors for monitoring your position on the Earth without the need for satellite communication with satellites. And then, and you know, and again, making use of techniques within quantum mechanics to secure communications along fiber optic cables. So there's something called quantum key distribution, which is being explored so that our, you know, whole sort of internet system will be more secure in the future. But yeah, I think it's still early days. We still don't understand, I think, how to think quantum mechanically. We still think very much in the way that classical computers do. And so I think to fully harness quantum computing, will ultimately somehow have to get better at thinking quantum mechanically.
Okay, so just someone who is able, like, tying with like quantum computing, said not sure about the future and, like, you know, impact on healthcare, so on. I guess one question we have was, what is the importance or your view of science or quantum computing applications for social change? The examples, areas of your passion or interest. So I think we have policy, sustainability, homelessness, and the safety of children.
Oh, these are just my list of personal areas where I would love to see technology developed to enable change for good. And I think one theme amongst a lot of these topics is that currently they aren't economically incentivized, right? It's, you don't make the most, you know, the jobs that pay the most aren't at companies that are looking to, you know, end homelessness, for example, typically, or, you know, with trafficked people, things like that. So, you know, we know that social workers are typically overworked and underpaid. So how do we change that paradigm? And I think that requires policy and government intervention, but also realizing that there's an economic case to be made. So just like with good company culture, and so we should maybe study that more and come up with KPIs that can be tracked, things like that. So, and, you know, until you're really studying the problem, you're not going to be able to solve the problem. So, and, you know, how much more productive could our economy be, for example? And so I'd be curious to know, you know, if you take quantum computing is actually a really good example. So there has been an extremely strong initiative across the globe. Many countries, governments are investing heavily in quantum computing. So we could do the same for these other topics or even blend them together. So there are initiatives around trying to marry things like machine learning and climate change, or AI and climate change, or quantum and climate change, right? So
Mhm.
could we do the same thing where we marry some of these new technologies, like, grants or initiatives, funding initiatives, to marrying new technologies to these kinds of problems?
That's great to hear. It's like looking for the solution is like already starting to solve the problem. So glad to hear that.
Mhm.
See, what a follow-up question is, do you have any advice for others looking to get into any of these areas that attack, I guess specifically for women and historically included technologists in the field?
Yeah, I think in quantum computing, what's interesting is, there's a lack of people who are trained in the space. And there are, as I say, there are these huge funding initiatives to try to invest in the space. And so it provides an opportunity for people to get involved. And I think people automatically think about students, but I actually think that we're overlooking older folks who could be retrained easily. So just as there are these code boot camps, I would love to see sort of boot camps into, microwave electronics or things like that, or people who even have worked on microwave electronics in other domains of industry. And it wouldn't take too much to retool them to work in this new up and coming field.
Right, because they have that
Uh,
background knowledge of like working with the hardware, working in industry. It doesn't translate to staring at a computer screen all
yeah,
day.
Yeah, so I'd say it's, and it's, I personally feel it's never too late. I constantly hear great stories about people who, switched careers in their 40s or 50s even. So I think if it's something that you're interested in, definitely go for it. And I'd say, know your own potential, but if someone's really excited to have you work with or for them, don't overlook that.
Yeah.
And maybe in a little bit of time, it'll all become more clear to you whether or not that's your place. For people in positions of privilege inside this field or in other fields, I'd say, look outside the box to see potential. For example, a lot of companies will just post jobs on their own website. But of course, what does that mean? It means that the people who already work there, it'll typically filter to their network more than outside of that. So if the people who are already working there don't represent the demographic that you're looking to transition to, then maybe you need to think about posting the job in other places that will
Like
reach
on Women
more
Who Code careers.
women who code, exactly. And there are, of course, other women in tech groups. There's also, Indigenous in tech, things like that. And I think we're all rewarded for that. Diversity of thought rewards companies. Ultimately, it's been shown that we're better at problem solving when you have people who get to the same right answer but come about it in very different ways. Yeah, I think also, and I've been on both sides of this, people are generally very excited when somebody is very excited about what they do and to work with them. So I've never applied somewhere where I hadn't already spoken to somebody there and done some research about what they do and been excited about what they do. So I would say a lot of people are pretty open to being cold called and messaged if you're like, hey, I did some research and I found your company and you work on this thing and I read this article about that thing and it's so exciting to me. How do I get involved? Can I have a few minutes of your time? I can't remember anybody who's ever said no.
I do the same
And
thing.
yeah, I think, and I mean, it works both ways, right? Like if you're just blanketing various
Just sounding like,
companies,
yeah, just saying like too
it's
general.
you're sort of maybe operating from a place of fear also rather than a place of excitement. So maybe just take a moment to check in and take a step back and go, what am I really looking for here? What do I really want to be doing? And then focus in on that. Find the people, talk to them, find the companies, and be a little more targeted, I'd say. Yeah, and I think people hate the word networking, but just forming connections with other humans can plant seeds that may take years to grow, but sometimes they flower at times in places that you weren't expecting and provide wonderful opportunities. And it was just because you had a natural connection with somebody. So I don't think of it as networking. I think of it as, oh, this person and I like the same cookies at this booth at this conference, right? And then a friendship grew, and years later, it turned out to provide an opportunity for, one of us or both of us. So I think, yeah, just going with the flow, following your nose, and, where you have a natural inclination towards a type of work or a company or people, I think it's always going to point you in the right direction.
This is great advice.
I think also finding companies who value people like you is important. When I was younger, I didn't really think about this, but for example, I've had to come to terms with the fact that I do well when I'm praised for doing well, and if I only ever hear criticism when I do things not as well, and I don't really get any praise when I do things well, then that's just not a paradigm that works for me. And just knowing that about yourself and knowing, okay, I need to find a boss who is the kind of person who will praise me, right? Because not everybody does. Everybody has a different style, right?
For coders who are maybe interested right now in quantum computing field, are there any programming languages you and your teams use, and could be considered like a transferable skill into these projects and spaces?
Absolutely. Python's extremely common.
Okay, that's good to hear.
So there are these multiple platforms now where one can go and program quantum computers. So IBM has a platform called Qiskit, and they are using it's Python based. And there might be other versions of it. I'm not sure. There might be, say, Java and C++ versions of it. But I know for sure we typically are using the Python or Python-esque implementations. And D-Wave also have these, their SDK is called Ocean, also Python. Again, they might have versions in other languages, but I'm only confident in the Python. So certainly, and Python's a relatively easy language to learn. If you already know C or Java, I'm sure it would be relatively easy to pick up. A lot of my data science colleagues work in other languages, R, Stata, those kinds of things, or knowing, MATLAB. I think those are all useful in that space. And then, of course, being able to use tools in that sphere, TensorFlow, those kinds of things, right?
Yeah, and I'll add a note from our data science as well. It's like also storytelling with the data, like recognizing what you're looking for and how to measure it so that, like you said, like it's relevant to the question.
Yeah, I mean, nothing beats a great visual. And it can take so long to make the perfect visual, but it's worth it.
Okay, and so what made you decide to be an astronaut with the Canadian Space Agency in 2016? And what's the feasibility of helping more women and historically excluded people travel into space?
So in 2008, the Canadian Space Agency put a call out for astronaut recruitment, and a friend mentioned it to me. And I actually realized that I would qualify once I was done my PhD. So in 2016, when they did their next recruitment search, I was in a place in my life that it was okay. It made sense for me and my family. And I thought, why not? At that point in time, actually, the Canadian astronauts were living in the US and working primarily with the American astronauts. But the only shuttles that were going up to space at the time were in Russia. So they spent half their year in Russia.
Wow.
So it was a very demanding in terms of lifestyle, we'll say. But, at that time, there still hadn't been any female astronauts. And it just sort of appealed to me to think like, oh, maybe I could be the first as well. There are definitely, more women now, but we're getting there, and other minorities. What's really interesting to me is that so recently, I think it was in 2019, the European Space Agency did a selection round, and it was the first time that disabled people were actually able to apply with certain types of disabilities. So we're really moving towards enabling more people to fulfill their passions. And ultimately, I got to maybe the top 100 out of 3,500 candidates, and was weeded out at that point. But now I'm in a place in my life where it doesn't really make sense to live such an adventurous lifestyle, but it's still very interesting. And now there are a lot of initiatives to build a moon base on the moon. they're going to be decommissioning the International Space Station and building a new deep space gateway that will orbit the moon, I believe. And actually what's coming up now are challenges in physiology. That's really what's blocking us from going too much further. So the way that our bodies are really not that well suited to space, and how we're going to overcome that is probably the biggest hurdle for space exploration at this point in time. And I remember actually back in 2013 when I was leaving academia and exploring different companies to apply to, I actually applied to SpaceX as one of the companies. And
Oh,
I
wow.
remember looking at the job postings and seeing at the time that there was a job posting for spacesuit designer. And so I thought, that's where they're headed. Okay.
So on a tangent, so that do you have a favorite space-related film or TV show?
Ooh, my favorite movie is The Arrival, actually, which
Okay.
is about aliens coming to Earth and attempting to communicate with us. And it revolves around the story of this linguist and her attempt to communicate with them.
I think it's based on the Ted Chiang, I pronounce it, the novel.
Yes, it's a
Yes.
short story.
Yeah.
But yeah, I love a lot of the stuff that happens in space, but oftentimes I find I do have to turn off my physics brain because so often things aren't quite right.
Like I can see that point and this year. So yeah. Do you want to share an example? Get it off your chest.
Oh boy. Well, I mean, I have to say it's not easy to try to come up with a visualization for the inside of a black hole or what a white hole might look like, or even be experienced like, because it's completely theoretical. But certainly it doesn't look like a library with a bunch of books. So that was definitely one visualization. I won't call out the movie. I'm sure if you've seen it, then you know what movie this is. But yes, you will not find a library inside of a black hole.
Okay, so when there is a movie with like once we know what the black hole looks like and the movie does have authentic, that's like, yeah, Danica will enjoy this movie. I'm gonna start wrapping up. So Spirit of Women Who Code, applaud her technologists to watch. You mentioned you had someone you'd like to applaud and highlight for their contributions to these fields, and I believe who pronounced the name correctly, Aggie Branzik. Yeah,
Yes.
and I'll just read her profile. So she has been great at disseminating information about things quantum via LinkedIn and opening the field of quantum for women and minorities.
Yeah, she's at the in Waterloo in Canada at the Institute for Quantum Computing, and I see her great posts on LinkedIn all the time, and just very inclusive.
Shout out to Aggie.
So for the next Women in Who Code technologist to watch, I will nominate her.
It's great to hear it's women helping support other women. So it's great to hear that. So for closing, so Danica, where can we learn more about you or follow you online?
LinkedIn is probably the best way. I'm keep a low profile online generally. I also, if you want to look at my publications on the archive or via the Bank of Canada's website, I have a profile on the Bank of Canada's website with my publications linked.
It's very cool.
I don't do any of that Twitter or fun stuff.
And I'll just like repeat again, it's like, so it's Danica Marsden, Marsden, to find you online. That's great. Yes. So thank you, Danica, for joining the show. Thanks for everyone for joining the Women Who Code podcast. Hope you have a great rest of your day.
Thank you.